Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'm going to talk about high-dimensional data was the title, but really it's about high dimensions. I'll put data here. So as these talks go, I mean, you won't find anything sort of cutting edge and new in this talk. So if you're hoping to do that, it's not the right one. But hopefully you'll find, all the things or sort of general perspective. That's what I aim to give. High-dimensional data. So high dimensions is just normal d-dimensional space. So d is always the number of dimensions. So I made the title and abstract a bit jazzy by asking some questions. I'll come to them in a minute. But first, before that, I want to discuss sort of the history of, in a sense, the history of this stuff. Not the history of high dimensions. They've been around for a long time. I mean, they've always been around. So, except, I mean, it's only been 3 so far, mostly that people can think of. So up to the, I would say, 40s or 50s, right? Mainly D was maybe 6 or 7 or something like that. These are all slight exaggerations. But 6, if you include in physics, 3 position coordinates, 3 velocity coordinates, is 6. Let's say our time maybe 7, right? But usually one dealt only with vectors which are 6 or 7 dimensional. Then why did we start dealing with higher dimensional vectors? Of course, in mathematics you can make up problems with very high dimensions, but the question is, what's the connection to reality? Why was this made up? I would place this probably in the 50s and 60s. Linear programming came along. And Danzig and others developed this. Now, I won't necessarily tell you, I mean, I won't recap what linear programming is, but roughly the idea is this, right? If you had a factory or something like that producing D goods, D types of goods, right? And you want to determine how much of each to produce. And those are your variables, x1 through xd. So this is automatically a d-dimensional vector, right? So you want to figure out the correct d-dimensional vector so as to do something, so as to optimize, so as to do something that you want to do, so as to satisfy your constraints or demands or whatever, right? Therefore, you started thinking about these as d-dimensional points in D space. So each possible solution is a point in D space. Now D, of course, could be very large, right? I mean, originally people didn't solve problems with very high D, but if you had actually this is an interesting thought, because if you had these command economies where people planned with the whole economy, if they had better linear programming solutions, maybe communism would have succeeded, because they could have planned exactly what to produce. But as it is, they couldn't solve problems with more than 10 variables, let's say, and it failed. I mean, by now we can solve problems which are very large, but those days they couldn't solve problems which are very large. So the state of the art in linear programming is now you can solve problems with D in the tens of thousands or even hundreds of thousands, right? How do you input the data is another question you might want to think about. So suppose you had a, 10 to the 10 size matrix. How do you type in the data to solve the problem? Of course, they can solve the problem once you typed it in. How do you do that? So we'll come to that. We'll actually see how you might think of typing this in. So that's in the 50s, linear programming, 50s and 60s, 70s. Let me just see what happened in the 70s. I have little notes here. Okay. So in the 70s, people started formulating combinatorial problems, and this area is called polyhedral combinatorics, and I'll describe this. And I would say mainly due to Jack Edmonds. But I'm going to describe it as a problem that perhaps all of you are familiar with, which is the traveling salesperson problem, right? TSP. And TSP is to, I guess you all know what TSP is. So, but here, let me put down. So this is a graph, and you want to visit each vertex once and precisely once. You might go on a tour. If I'm lucky, there will be a tour. Of course, there is a tour. I guess this is the tour. These are now 6 vertices, and there are possibly 6 factorial tours. I mean, there are less than that. You can easily eliminate some possibilities. Now, I'm going to do something pretty perverse to represent the traveling salesman problem as a high-dimensional problem. In the beginning, the examples I'm going to give, including this, are going to be, you would think of this as something you should not do. That is, we are going to increase the number of dimensions. We are going to formulate problems in much higher dimensions than we need to, right? So this problem with 6 vertices is a problem with 6 variables, right? So if I specify the order in which I visit them, then that is done. So there are 6 degrees of freedom, or even only 5 degrees of freedom, if you will. So if you have n cities, there should be n degrees of freedom at most, right? So it should be an n variable problem. But let me do something terrible, which is formulated as an n choose 2-dimensional problem, right? Which again, on the face of it, is a stupid thing to do. So here's the n choose 2-dimensional problem. I'm going to take each tour, there are n factorial possible tours, and represent it as a 0, 1 vector, and I'll do it mainly by example. So let's number the edges. This is edge 1, edge 2, 3, 4, 5, 6, 7, 8, 9, and 10. There are 10 edges in this. I'm going to put down a 10 vector corresponding to this tour. I'm going to say the first edge is traversed is in the tour, second is not, that is, third is not, fourth is not, fifth is, right, sixth is not, seventh is, and so on, right? I'm going to put down a 0, 1 vector. Again, this is a seemingly perverse way of representing the tour, right? I could have instead just told you the order in which I visit the vertices. But I'm going to go out on a limb and put down a 15-dimensional vector. 6 to choose 15, so there could be 15 edges, although here there are only 10 edges, but maybe imagine all the 15 edges being there. So I'm going to put down a 15-dimensional vector with zeros and ones. 1 if the edge is in, 0 if the edge is not in. Okay. Again, wasteful. And I'm going to, my proposed method of solving this problem, actually Edmund's proposed method of solving this problem is the following. Suppose you have n cities, you go to n over 2-dimensional space, you put down the n factorial points, each is a 0, 1 vector. These are the possible tours. So each tour becomes a 0, 1 vector, like this tour became that, right? And those points are going to be like this. And I'm going to do linear programming over the convex hull of these points. Now, before I do that, maybe I'll lapse back into linear programming and tell you quickly why the geometry is important. So it came from factories and goods. How does the geometry come in? The geometry comes in because if I have linear constraints, I can represent them like this, right? And if my objective function, so my profit that I'm maximizing, let's say, is also linear, so it's level, this is a level curve of the objective function. I want to make it as high as possible. You can all see from the picture that a vertex would be a maximum point, right? As I move this level curve up, the last point it would touch would always be a vertex. It could be more than a vertex, but it could always be at least one vertex. So Danzig's algorithm says go from vertex to vertex till you find the best. So maybe you started here, and perhaps you're unlucky and you took this route. You go from vertex to adjacent vertex. Finally, you come there and it's optimal. Okay? I won't tell you how you detect it. Now, Edmund said, let's do the same thing for the TSP, for example. You put down an n factorial vertex polytope. N factorial is exponentially bad. It n choose 2 dimension, which is also bad. And you walk around the vertices of this polytope till you reach the optimum, which is very bad. Right? Now, interestingly, I'll tell you the punchline before I tell you how it might even be possible. Currently, people can solve several thousand city traveling salesman problems. Not all of them, only special ones. And some of the people that solve these problems, Bill Cook, David Applegate, and Kautal, and so on, they can solve even tens of thousands of city problems. The amazing thing is they can tell you that what they found is certifiably, completely, correctly the optimal solution. Right? I mean, there are 3,000 cities. You're sitting in this many dimensions. Possibly there are 3,000 factorial tours. Right? They can say among all of those, what they've found is absolutely the optimum. There's no doubt, no probability, no doubt. And they do it by using methods like this, by imagining the polytope in this dimension. So how does this work? Right? Of course, I won't tell you all of this, but why did you increase the number of dimensions? Well, you increased it because it turns out, while this polytope is bad, it can always be enclosed in a polytope which is much nicer. Okay? And it's bigger polytope than this, but it's a nicer polytope. Can you have that? Yes, you can have that. For instance, inside a cube, there might be a very, very bad polytope, right, with a lot of sides. So your original polytope might have n factorial vertices and more than n factorial sides, but maybe the enclosing polytope, they can always find a nice one, it turns out. Okay, I won't tell you what that is. They can always find a nice one. Then you do Danzig's algorithm to optimize the Tor length. The length of the Tor is a linear function, right? It's just a sum over all the edges of the length of the edge. And if the length of this edge is L1, this is L2, I just take this times this times this, and sum it up. So only the edges in the Tor will contribute. So I optimize over this big polytope, which is very nice, and say this is my optimal vertex. But then I realize it's not in the polytope I'm interested in. It's not 0, 1. Then it turns out, it's sitting in these high dimensions, you can always find what's called a cut, which will cut off the current point, which shouldn't be there, but will not cut off any 0, 1 points. So all the Tors that should be around will still be around on this side of the cut. And what you currently have as the best will go away, will be chopped off. And it turns out, then you can optimize over the cut thrown in here and keep going. And it turns out after a reasonable number of iterations, you'll get absolutely the optimum because you'll have no more cut. You'll have found the 0, 1 thing, and that is the optimum. Okay. I mean, again, it's not important that I get all the details across, but this is sort of the general picture. And 15 years ago, 20 years ago, maybe not, maybe 25 years ago, if you had said this would be the way to solve several thousand city traveling salesman problems, I would have laughed at you. So would have everybody else. But these are the champion methods to solve these problems, right?
What is the intuition?
The intuition is that it turns out you can always find fairly good cuts, families of cuts. So lots of work has gone into finding families of cuts. There are subset inequalities, there are comb inequalities, there are tooth inequalities, and so on and so forth. Each of them is a paper. And then, so lots of papers later, you have lots of families of cuts. And there's some nice data structures involved in keeping track of these cuts and so on.
So the complexity of this algorithm depends on the number of sides that the bigger polygon has, right?
It depends on a lot of things. Yes, among that number of sides. But okay, so here's, maybe I should tell you, I should address that point, which I sort of hinted at. So how do you enter the data to solve such a large problem, right? Even though you can solve it, how do you enter the data? Similarly, how do you put down all these facets? Well, you don't. In both these problems, you do what's called constraint generation. On the fly, you generate whatever constraint you need. So you've got a number of constraints, not all of them. You've got a few, you optimize over that, and then you realize that's not right, and you generate a cut. And then you keep going with that. Okay? So one of the guys who solves this problem, David Applegate, was my student, and he was, it's an interesting story because in the 90s when they were, D.E. Shaw, the company was realizing that computer science PhDs can make money, he was offered an extra digit for a salary, and he turned it down and started solving TSPs at one less digit, which is quite nice. Significant digit, actually, because okay, so that was one example where you increase the number of dimensions and that bought you something. That's what? Now that's 70s. Each decade receives one bullet at most in this picture, right? 80s is something familiar to a lot of you, perhaps. Now here you went down to square number of dimensions and that bought you something. Okay? What I'm going to tell you in the 80s would have been an even greater surprise if I told you now that it was something that went to infinite number of dimensions. And in practice, it's very useful. I don't know, some people in the audience can guess what that would be. What is it in the 80s that, Pratik? SVMs, right? I mean, I'm going to talk about SVMs. So machine learning people will know what this is. So I'm going to talk about SVMs. So what happened in the 80s, Vapnik came up with this brilliant idea which is the following. So this is to do with machine learning. So you're given examples of points. I mean, so again, maybe I should go back a step. So usually machine learning for a long time, whenever you heard a talk, you thought it was the subject of learning chairs, because they always give the example of what's a chair and what is not a chair. So, you know, if I want to describe a chair, in most machine learning talks, they would say, I can put down a, I don't know, 500-dimensional vector, 500 features, and I tell you its height, its weight, and how many legs it has, and so on and so forth. These are the features. And I tell you for those vectors whether each of the vectors corresponds to a chair or not. So I give you a bunch of chairs, which are called positive examples. So they're really just points marked in 500-dimensional space, with plus for positive, yes, it's a chair, and some other examples marked with minus for no, it's not a chair, right? And that's what's given to you as data. And what you have to find is something that tells you a chair from a non-chair. And here in this nice picture, you have a linear constraint which says above that is all chairs and below that is not chairs, right? But the picture need not be necessarily so nice. The picture may be like this, and I intentionally will draw it like this. All chairs may be sitting below this curve, and all non-chairs might be sitting above this curve. I can't put a straight line separating the positives and negatives. But perhaps I can put down a polynomial. Maybe this is a polynomial curve. Which separates the two. So more, let's say a little bit more. So this point has d coordinates. If I'm thinking of polynomials, I take this d coordinate point and I make it a d squared coordinate point. I put down all these coordinates, but in addition I put down products. Pairwise products, let's say. Okay. I could put down products of 3, products of 4, and so on, right? And maybe once I do that, then there is a linear separator. So roughly, intuitively, if there is a separator which is quadratic, once I put down these many coordinates, that becomes a linear separator, because a quadratic function is just linear once I have products put in already, right? So I can look for a linear separator in this higher dimensional space. So the point of increasing the dimension of the space here is obvious. As I increase the dimension of the space, I hope I'm more likely to have a linear separator between chairs and not chairs, right? So why stop at degree 2 polynomials or degree 3 or degree 4? Why not go to infinite degree polynomials? And in fact, probably the most frequently used, I'm not a machine learning person, so don't quote me on this. The most frequently used embedding is to Gaussian kernels, which is actually infinite dimensional embedding. So you take these points and put down, in some sense, all polynomials, formed by taking finite products of these. And in that space, there will be a linear separator. And it turns out that that works in practice very well. Okay? Because you don't put down, again, same question as generating the data, you don't put down the infinitely many coordinates.
So
yeah.
Is this transformation to higher dimension something that people are doing more recently, or is it?
Okay, so I guess, I'm not an authority on this. Anybody can jump in and add something. 80s is probably when you saw sort of the first use of this in practice, whether people always in mathematics embedded points into higher dimensional space and that brought you something, but in practice this was probably the first use of it.
So in practice, as in you could actually write programs that could.
The machine learning people do this every day. They have Gaussian. Oh, you don't write down. Actually, so you don't write down the embedding just like there. You don't write it down fully. It's implicitly written down.
Okay.
Which I mean, it's too much to tell you how to in this talk to say how to. But the conceptually it is thought of as embedding in a higher dimensional space, possibly infinite dimensional. That gives you something. Yeah.
The useful embedding is actually looking at something like pairwise products or k-wise products.
Well, I mean, the most useful embedding is, for instance, the Gaussian kernel. So it turns out if x and y are your 2 points, that is an inner product in an infinite dimensional embedding. You have to show that. It's a couple of lines.
Coordinate is sigma.
Well, no, the coordinate is all monomials consisting of products of finite number of coordinates of the x's for the x and the y. Yeah. I mean, you just have to do the series expansion of that. And then there are a few lines of proof you need to show this. And you don't actually write down the embedding. You just need inner products. That's all. Okay, so that was the 80s. So what about? So I think that's. I mean, this is your history, and then yeah. So good. So far I have no probability really. Although this the Wapnick's work comes from empirical process theory, which is really probability and statistics. But so far, at least in the algorithms and in my talk here, I have not mentioned any probability. Just geometry, right? Things blew up dimensions as vectors. Oh, I see. Okay, so now we should switch to the second color. I knew a good mathematician once who actually never erased. She just wrote on top of that. And somehow it seemed to work. There were gaps. Yeah. So far, no probability. And now I'm going 90s and beyond, because we are doing only one little bit in each decade. So this I'm going to do with an example. These things I talked about are really broad areas. I mean, it's not only TSP. Edmonds actually did this for another problem called matching. Polyhedral combinatorics is a big area. In fact, a lot of problems are solved using this type of method. It's mainly been confined to operations research. By the way, one of the reasons I picked this is that I thought maybe a lot of you will not be familiar with this, because in computer science it hasn't received as much coverage as perhaps it could. There aren't too many computer scientists that use polyhedral combinatorics for doing optimization. The rough reason is the viewpoint is different. See here, as I said, these guys get the exact optimal solution for specific TSPs, for benchmark TSPs. But of course they can't solve the worst case. And what the CS viewpoint is, I want to solve certifiably the worst case, but I'm willing to make quite a bit of error, because otherwise these problems are NP-hard and it's very difficult to solve. But they solve benchmarks that come sometimes from real applications. Sometimes not. Well, TSP is applicable in a lot of things like VLSI wire. I mean, to route the soldering. So if you want to manufacture an integrated circuit and you want the soldering the instrument to move as little as possible, yet solve the endpoints, because it has to do that repeatedly, you solve a TSP, right? So some of those TSPs are very large, and people can solve them using such methods. So probability came in the 90s, and I'm going to introduce this. There's also an area, but I'm going to introduce this with one problem that's often introduced with, which is analysis or statistics of NetFlow data. What is this? So you have a large network, and here's perhaps a central database, and various routers or any sort of parts of the network write in logs of data, logs of messages. And the logs might contain a few pieces of information. Perhaps it contains the source, destination, and the number of packets, right? Perhaps a couple of other things, but maybe that's all. Okay. Now, let's ignore the destination part for a moment. Let's say that it writes source and number of pairs, right? And at the end of the day, I want to collect statistics. I want the, for instance, I might want the total number of packets traversed. That's not very difficult, but my model is this is huge, and this data can only be streamed. And streaming data, again, the abstract model is, this is my imitation of a stream. It's just flowing by the data, and you're sitting here analyzing. And perhaps your RAM is very small. So you can look at this data, all of it once, but not really store much of it. Space is very limited. And so you have to sample on the fly. Another little technical phrase we can introduce. Basically, the point of the model is your RAM space is much, much smaller than data. You can say polylog, for instance, of the data, right? And you want to analyze this data. The one thing you might want to find, the first thing you want to find is total number of packets over the entire day. That's trivial. I just keep a running total, right? I don't have to see all pieces of data. I take a running total, and that's enough. Okay. But the next piece is a little more difficult, and I want to find the variance. between the sources, right? I want to find the sum over all sources of the mean squared deviation. Okay. Now, the reason it's difficult is that you don't have space to sort the thing. This is all written by various processes in arbitrary order as the messages came. So the messages from the same source may be written all over the place, right? And you have to take the sum and then square it. Okay? So how do you take the sum and square? Well, on the face of it, you have to remember what's the total for each source. You have to keep a running total, and then at the end you can square it, right? That's too much space. We want to do it in logarithmic space. That is n space, where n is the number of sources, right? So I don't want to do each source and then add up. Okay? I'll tell you a worse problem. The worst problem is, suppose you have two streams, one for day 1 and day 2. And you want to do a comparison. So you want to do the traffic for source I on day 1 minus day 2, and then square it, right? And then add. This is your variance between days. And that'll be good to know because, you can, if there's huge variations between days, you would like to know that, right? Now, this is much worse because I'm going to insist that you find this to relative error. Okay, 1%. Now, one nice thing to remember about relative error is the following, right? If you're trying to compute a quantity, which is 0, the relative error allows you to make no error, right? This is very important to remember. It's a nice way to remember relative error, actually. So if the quantity is very high, then you're allowed a lot of leeway. If the quantity is 0, you're allowed no leeway at all. You have to get the exact answer. What's wrong with that? Well, what's wrong with that is these two numbers may be very big. So this may be 1 billion, and this may be billion minus 1. Or even, it may also be 1 billion. Okay. Now, any solution you might think of will say, take some sampling, do something. Sampling is terrible because you would estimate 1 billion to some error and the other billion to some error, and the difference is going to allow you no error, and you'll make a lot of error, right? So this won't do. But here is now what again seems like a perverse way of doing this problem. You imagine the whole data for each day, let's say the data for each day, as a point in n space where n is a number of sources. It's a vector. Let's call it a vector. So n could be in the hundreds of thousands or whatever you want. So it's an n-dimensional vector. And for the variance part, let's say, the mean squared error, I want to find the sum of squared components. So this is the vector where I have this. Vi is the total number of packets from source I. Okay. I haven't found it. I have not been given it. But let's imagine that vector, and I want to find the length of this vector. But length is sum of squares, right? So sum of squares is what you want for variance without all the details. I want to find the length of this vector. So I imagine this as an n-dimensional vector where n is very large. I cannot write this down. I don't have space to write it down because my RAM is very small, and I want to find its length. Okay? And if nothing else in this talk, I'll give you one theorem, which is a very beautiful mathematical theorem, which would be nice to remember. This is a theorem of Johnson and Linden-Strauss. It's called the random projection theorem. So V is any vector in n space. Okay. Big V is a random k-dimensional subspace. This one theorem I'll write down a little more rigorously. Then the length of V projected onto this, and I'll draw a picture, is almost certainly V times root k over n, without giving you details. So what is this saying? Let's imagine k to be 1. I have this vector. I choose a random one-dimensional space, which is just a random line. This is the origin. I put a random line, and I project this vector down here to this random line, and take this length, and it says it's about 1 over root n times that. Now, why 1 over root n? Because Pythagoras theorem works, right? So there are n components, and if I add them up in square, I will get that. So that's why 1 over root n, because it's Pythagoras, right? The squares add up. The vectors don't, the components don't add up. Now, in 2 dimensions, this is false. So what that would be saying is you have a vector v fixed. I pick a random x-axis and a y-axis, and I project, I should get about 1 over root 2. That's the same as saying this angle is about 45 degrees. Okay? That's not true. So if I have a random, arbitrary vector, fixed vector in 2 space, I pick a random set of coordinate axes, any angle is equally likely, not 45 degrees, anything between 0 and 90. Okay? But the theorem is saying 45 degrees is the preferred angle, and it's almost certainly going to be close to that, which is true in higher dimensional space. It's not true in 2-dimensional space. So this is only true if the number of dimensions is very large. So one other reason to boost the number of dimensions is you buy things like this, that you get nice theorems like this. Okay? So the way to remember this is fixed vector. I choose arbitrarily my coordinate system. I'll be at 45 degrees to the vector, the x-axis, if it was true in 2 dimensions, which is not the case, right? So instead of estimating the length in n space, it says I can estimate the length projected to some random k-dimensional space. K is much smaller than n. Okay. And that would be sufficient. So that seems simple now. I just pick a random k-dimensional space, keep it with me, and do the projection as I go along. I can do the projection on the fly. It's not difficult to see. That's just a dot product. You can do dot products on the fly without going into details. Okay? But that's not quite right, because even to keep one vector takes n space. Which you don't have in RAM. So what you have to do is keep a pseudo-random vector. Again, I won't go into the details, but let me step back one step and mention that this random projection theorem is immensely useful just because of this length-preserving property. So it really is saying that any very high dimensional vector, you want to know its length, then you project to a random low dimensional space that's enough to measure the length there. Okay? Because you know this factor, you can always correct by this factor and you get the correct answer. Yeah. Among the many uses of it, it'll be nice to mention something that Nikhil Srivatsava here in his thesis worked on, which is called graph falsification, where it turns out it's interesting to pick, wake him up, it's interesting to pick, that's fine. It's interesting to pick, there's one trouble with not having slides is, with slides you can go to sleep because it's dark. Without slides it's a major problem. Not for the speaker, but for the audience it's a problem. But so, in what Nikhil's work, then you have to sample edges of a graph with probability proportional to the electrical resistance, if you imagine them to be resistances. And that turns out to be something to do with high dimensional vector lengths, which you want to estimate. And instead of estimating in the high dimensions, enough to project to a low dimension. So, in fact, that's the context in which it's often used, and it's very useful for a lot of problems like that.
You have to estimate n nodes, right?
You are told n, let's say. But you don't have to be. You can estimate. You can keep a running total and update your, I mean.
You don't have n space. How do you estimate n?
No, you keep a running, log n bits are enough to count.
Oh, right.
I mean, so yeah, everything can be counted, but you can't keep tally for each one. Yeah.
But if the same source keeps coming many times,
Yeah.
then you have to know that it's the same source or different source.
You don't have to. Okay, it's a good point. So, in fact, what happens is, see, you have a random vector, let's say, on hand. The random vector has a particular value for that component. You just multiply the number of messages of that source by that and then add up. Okay? But you do have to know that that component of the random vector is such and such. How do you know that without storing? Well, you have to do you have to generate it on the fly each time with your pseudo-random seed. So there's a few things that I'm sweeping under the rug here. So this is actually one good way to do what's called dimension reduction. So in the beginning of the talk, I started with dimension boosting, dimension increasing, but that's not intuitively what you want to do. You want to reduce dimension often, right? So this is one method to do dimension reduction. You randomly project. It has a nice property that length is preserved, but it actually doesn't work in all contexts. So here's an important context where it doesn't work, and you have to use some other method, which is also probably familiar to a lot of you who work in the area, but let me just mention it. So a context it doesn't work is the following, is a clustering problem. So here's a picture that I'll draw without much explanation for now, and then perhaps explain it later. So I'm sitting in n space, and not a very good drawing because it's only a two-dimensional drawing. Each of these annuli corresponds to a Gaussian. This is Gaussian 1. This is Gaussian 2. And I'm picking samples according to each Gaussian, and believe me, those samples look like this. They lie in a very narrow annulus, pretty far from the center. That is the center of all of them, but they lie pretty far from the center, right? Again, the analogy that I give for this normally is like a planetary system. The center is the sun, if you will. These are the planets, but they're very far compared to the sizes. So this is true of d-dimensional Gaussian. So if you pick points with reasonable parameters, if you pick points, they'll lie in a very thin annulus all around a center, but very far from the center compared to the width of the annulus. Okay. You might be interested in clustering, separating out the points from this. The difficulty is, of course, these points sort of sit seemingly in the space of the other center. So you might think of projecting randomly. In fact, that's one thing that people do often. So you pick a random line, and you'll say that I'm going to project everybody down perpendicular to like that, right? And so on. And you hope that that helps you, but unfortunately it doesn't help you. Why is that? So I take this point, this is the center. Center 1 comes down here. Center 2 comes down here. Okay. The distance between them in the projection is actually, but for this factor, related to the distance between them in the big picture, right? Because this is a vector, and I'm projecting down. I'm projecting that vector down. So these lengths are very related. Okay. What am I trying to do? I'm trying to separate out the two Gaussians, so I'm hoping that compared to the distance between the centers, the distance between them will be projected out, but unfortunately that's not the case. All lengths are preserved, right, to the same ratio. So it's as confusing here in the projection as it is in the big picture, unfortunately. Okay. So that's not a good thing to do, but here is a good thing to do. If I could project, so this is the other projection that's often used, if I could project to the line joining centers like that, now what happens? Now these guys get projected like this, and I'm going to draw the density, and the centers stay as they are. So I'm going to draw the densities. So again, you have to believe me. So if the standard deviation is sigma, it's a standard parameter, the picture in the projection looks like this. This is one Gaussian, that's the other Gaussian. That is, if the distance between these two is a few sigmas, the distance between this and those points are also a few sigmas. So all of them are comparable ratios. In the big picture, this was more like square root of the dimension times many sigmas away, because you sort of had one sigma in each direction. If each dimension, if the number of dimensions is very large, the number of sigmas becomes very large. It goes as a square root, again Pythagoras. Okay? The details are not important, but what I want to say is a random projection is not as good as projecting to the line of centers. Okay? But that leaves a big question of how do you find the line of centers? And it turns out this is a very nice theorem of Wempala and Wang. And the theorem says that if I do PCA, which a lot of you are familiar with, principal component analysis, which comes from linear algebra. So you have to do some linear algebra on the data matrix. Not precisely what maybe we won't go into, but standard linear algebra. If you do that, you can in fact find the line of centers. So that's another way to project. These are called the principal components without going into details. So let me just say principal component projection is the alternative to random projection. This is one way of dimension reduction, and random projection is the other way. So history-wise, we saw that in the first few decades we increased the dimension. In the next few decades, people have been trying to reduce the dimension. And there are really only two main methods of dimension reduction: principal components and random projection. Principal components uses the data to figure out what are good directions to project. So for instance, the line of centers very much comes from what the data looks like, but it doesn't have this nice property. It doesn't have this nice theorem that lengths are preserved. Okay? So this projection will make different lengths look different. Whereas random projections preserves lengths in this nice, but nothing to do with the data. It's just random. You pick it out of the hat, whatever the data is, and project down. And even then, it turns out to be useful in a lot of contexts. Okay, so now so I have to give you, I usually try to give a choice, which is either questions or several more minutes of talk, not hours, but questions or possibility. Otherwise, I'll launch into one more topic so that we don't run out of topics. I mean, I think it's decent to finish 10 minutes before, but not long before that. So I have one more topic for 5 more minutes or 6 more minutes, unless somebody is brave enough to ask questions.
Is there anything in between?
Sorry?
Is there anything between?
Oh, anything in between these two projections. So not any general method that I know that does dimension reduction. So there are embedding problems. People try to embed in lower dimensional space without dilation. So, but generally no. Okay, so I think you, unfortunately, I've bargained for one extra topic, which actually I listed in the thing, but maybe I can. Or this doesn't erase. So let's try this. I'll try to finish in 5 or 6 minutes.
The right side erases the best.
Right side is more erased. Yeah, you're right actually. The next tea talk would not have any board to erase. So okay, the last topic has to do with some geometry too, and perhaps the best introduction to this is starting with something classical that you all know: computing areas and volumes of solids and 2- and 3-dimensional pictures, but not of necessarily very nice things. So if you have object in 2D and you want to estimate its area, it's not precisely a polygon or something, triangle or something like that, where you can do in closed form. How do you do this? Well, I mean, you can do many things. One thing to do is put a grid down and count the number of grid points inside, and that's an estimate, right? I mean, hopefully the grid is fine enough that gives you a good estimate. Sometimes, well, in D space particularly, this is very bad if D is large. So in D space, there are exponential in D number of points probably, and to enumerate all of them would take you a long time. So you don't want to be doing that. Instead, Monte Carlo method, which is classical and also very nice, is the following. You enclose this in a rectangle. And I know how to pick random points in a rectangle.
The input, is it again points or?
So the input, okay, good question. The input in these examples will be what's called an oracle, which this is a set S. You can ask it whether X belongs to S, and it'll say yes or no. So it's a very, not a closed form. So it only tells you after you ask. It's actually similar to the column. It somehow has a similar thing to the linear programming question, because see, I don't have a full description. It's too large. But whenever I want to know a particular point, I can work and get to know the answer. Yes? Right, okay, so it's going to become convex very soon, right? Right at the moment, in the next few minutes, it'll become convex. Yeah.
I mean, it's only solvable for convex.
It's only solvable. We only know how to do this for convex sets, yeah. So So here's what you can do. You can pick a random point on the x-axis, random point on the y-axis. That gives you a random point in the rectangle, right? So I pick a bunch of random points in the rectangle, and I see what proportion land inside. That's an estimate of the area. That's an estimate of the ratio of the two areas, right? Okay, fine. So here is the problem with d dimensions. So let me try to imitate this second procedure in d dimensions, or picking random points. So here, let's say I have a perfect sphere in d dimensions, and your multivariate calculus will tell you how to do multiple integration to get the volume in closed form. But let's forget that for the moment. This is a radius 1. I try to apply this method. So I enclose it in something nice. I enclose it in a rectangle, square actually, of side 2, and throw points at it and see what proportion land inside. And for those of you who don't know the answer already, what proportion do you think will land inside? Exponentially small, it turns out in d. So it's very, very small. So the volume of this is 2 to the d, right? The volume of the sphere is 1 over d to the d over 2. It's very small. It goes to 0 as d goes to infinity. So this procedure won't work because you'll never get a dot inside the circle until you throw many, many dots. Until then, so if you never see a dot inside, you must return answer 0, right? If you see 0 proportion inside, there's no better answer than 0. So you won't get an answer. That's not a good way to answer the problem. So instead, what we do is a random walk. And okay, now I'm going to draw a convex set. So this is only going to work for convex set. So I have a general d-dimensional convex set, and I would like to know its volume, right? Now, let me not worry about the volume. Let me worry about a different question, which is motivated by this. So I took random points, and I'm sorry that none landed inside the ball, right? So let me rework that into a question of just pick a random point uniformly at random in K. Inside, this is K, inside of it also. Let's only focus on that problem. Let me forget volume for a minute. Let me focus on that problem. There was a side problem when we were discussing volume, but let's focus on that. So we decided putting it in a larger object and so on is not going to work. So instead what we do is put a grid down. And do a random walk. Now, what's a random walk again without all the details? You start somewhere, and in d dimensions there are 2d coordinate neighbors. So here, north, south, east, west, right? You pick one of them, each with probability 1 over 2d. In 2 dimensions, it's 4 directions, so 1 over 4, and go to that. Go to the one you picked. Except you don't want to go outside because you're basically paranoid from this example of losing yourself in space and not coming back to where you're interested. So if you're here and you pick to go there, you don't go there. You see it's outside. You can consult the oracle, tell you it's outside. Then you just stay back there. So this probability is 1 over 2d, 1 over 2d, but you don't go out. That instead you stay here. Okay? So that's simple. That's a random walk, right? Each step, go to one of the neighbors equally likely, provided they're inside the object. Otherwise, don't. Okay? Now, in general, there'll be exponentially many states here because, along each dimension, you could have even 10 states, let's say. Then the total would be 10 to the d, potentially. So d isn't the exponent, right? So you don't hope to be able to see everyone. That's far too long. But the nice theorem is that in polynomial in d number of steps, you are almost equally likely to be everywhere, almost uniform. Okay. So the surprise here is that there are exponentially many states, you have hardly any time to see everyone, but after having seen only a very small number, the theorem still says you're equally likely, more or less, to be anywhere. So that solves the sampling problem. Since we don't have so much time, luckily, we don't have to explain all the details because it'll take a long time. But that solves the sampling problem, right? Now, how do you want to solve sampling problems with this high dimensions? I won't motivate this very much, but basically, if people are telling you that here's a complex system like a bridge or a rocket I built, the probability of failure is 10 to the minus 7, well, they're doing a calculation like this. They have some very complicated Gaussian in high dimensional space where each dimension corresponds to a component, failing or not. So your probabilities of failures of each component, you see how they behave, and that is some Gaussian distribution, and you take the failure region, which you hope is very small, because you want the failures to be very small, and then you compute the probability of the failure region. Now, the probability is like a volume. That's, in fact, that can be proved more rigorously, but it's like a volume or an integral. So you compute that and say it's 10 to the minus 7, so you tell the public this thing will fail only with probability 10 to the minus 7. Okay? Okay, I think I will stop at probability 1, and then you can, yes?
You have given only an oracle. How do you start up with the point in space?
Yeah, so you have to be given a point in space too. It's called a this is a good point. So if I give you a convex set in space and I'll only give you an oracle, you'll never find it, right? I mean, I can even play the adversary. I can keep saying no, So you have to be given a point. You have to be given a little more, but a point.
But not a random point.
No. Well, random point, then you would have been done, right?
How do you move around and follow these steps? How do you?
Well, every time you consult a membership oracle, yeah, you have to be given a well-guaranteed. Well, it turns out a membership oracle is enough. You have to be given what's called a well-guaranteed separation oracle for doing it simply. You have to be given one point and a containing ball or a contained ball.
So you take long jumps as well, because in polygisters you won't be even moving.
Yes, you have to do well rounding. For that you need. So what he is referring to is that the polyhedron may not be so nice. It may be a long, thin needle, and then my grid better not be like that. My grid better be like this, right? And so on. It should be very fine in that direction. So you have to do what's called well rounding. You have to transform there's always a transformation which sends the body to something nice. Yeah.
Is there a reduction from the Gaussian volume problem to this volume problem?
Or to just a volume problem?
Yeah.
No. But these methods work for all log concave functions, right? So no, there is no automatic reduction from Gaussian to this. It is true if it's the concave function, but it's only Gaussians and so on are only logarithmically concave, and so you can't reduce it.
So the convex assumption is necessary to think that if you give some fudge factor, it can actually do it for even moderately non.
Yes, you can do it for, there's a log concavity defect. As long as it's small, you can do it. So you need, so like the Gaussian is log concave, but if you need the logarithm of the function to be nearly concave, the concavity defect cannot be too high. And actually now more recently we know results that say how high it can be.
It's a bound limit.
Yeah. Yeah.
Is there anything like PCA for other non-Euclidean situations?
Okay. So actually the big thing is something to do with tensors, which is the immediate next thing. There isn't as nice stuff for tensors, but actually there is some stuff. So the basic question for tensors is find the first singular vector. So I don't know, maybe I won't tell you all the details, but basic linear algebra, a very important question is matrix A, find a vector x so that this is maximized, where I restrict the length of the x to 1, right? And for tensors, you can define a corresponding question, and that we know sort of very partial answers to. We don't know very good answers to.
I have one last question.
Yeah.
After that, I'll keep quiet. So you talked about varying the grid granularity around the surface of the thin period, right? Is this problem very similar to what they have for grid generation problem with solving differential equations? Is it?
There is the Euler's method for differential equations where you take a random. No, that may be slightly different because there you make sure. No, I think that's slightly different as far as I can. I don't know for sure, but yeah.
Because there's a big open area. People are working like
Yeah, numerical analysts and computer scientists. Yeah.
So over there, you said if you go out of the region,
Yeah, don't go outside. Instead, abort that choice. And
But can you dynamically just halve the step length to adapt as you get closer?
yeah, so actually some of the later algorithms do precisely that, because see, you don't know whether it looks like this or this to start with. You walk and find out. If it looked like this, you take the step size here and half it. Or if you're going this way, take the step size and double it. So there are adaptive algorithms like that. Now,
So how would you find out it looks like? How do you find out that?
well, I mean, if you're marching in a direction, you can find out the extent of the body in that direction. But
It might take you a really long time.
it might take you a long time. Yeah, one line you can, but not otherwise. So you have to balance your adaptiveness to how many steps you take to figure out.
So Low was an idea, sorry, I violated my agreement. Low was an idea to just jump over spheres, right?
Jump over? Yeah, ball walk. Yeah, right. No, I guess, yes, there's a ball walk too. So,
How do you intuitively explain that one?
well, okay, so we can, instead of doing this, I can be at an arbitrary point and I take a ball of that, sphere of that radius and go anywhere there, instead of going only on coordinate axis. So there are lots of things. I mean, this coordinate axis move, we call this Rook's moves instead, or King's moves rather. Rook's moves are where you could go anywhere like that, right? Those were, well, Gibbs sampling in statistics does what's called Rook's moves because of, and then what we did is only King's moves. These are, maybe you can call them Queen's moves, although it's not quite, but you can sort of go in any direction. So it's probably like a Queen's move. So I think my ride is going to leave in, when does?
Stay in the incline the whole evening.
Okay, thanks a lot. Thank you.